All right, let's continue. We'll talk about some properties. A couple things. So you may have noticed no more shadows. I waited a couple hours until the sun got low enough, so our videos will be a little bit easier to read. Also, I meant to mention this back in our first example when we did the definite integral from 0 to 8 x squared plus 1 dx. Some of you may have been thinking to yourself, or maybe everybody, when we perform that antiderivative, what happened to the plus c? Where's the plus c in the antiderivative? We make a big deal about it when we do indefinite integrals, but when it comes to definite integrals, turns out we don't need the plus c. So let me show you why. Let me show you it with the plus c, right? It turns out you could or could not use it, but nobody ever uses it, and here's the reason. When you do this antiderivative, right? For x squared, we had 1/3 x to the third. For 1, we had x, so 1/3 x to the third plus x. Let's imagine if we had the plus c there. And then we evaluate from 0 to 8. Okay, so we'll plug the 8 in, we'll subtract, we'll plug the 0 in. Okay, so plugging in the 8, plugging in the 0, and we got the c all along. Hey, what's going to happen with the plus c? Well, because we're subtracting, in any problem, it's always just going to cancel out, right? Plus c minus c. The c it always disappears because it's this, right? It's the same constant is going to subtract. So people realize this and they said, I'm not even going to write it here because there's no point. It's always just going to cancel. And so you never see the plus c in that antiderivative or here, right? So you just compute those numbers for the rest of it. And that's why we don't have plus c in these antiderivatives. Although it wouldn't be wrong, but you're going to get to the same answer. Okay. Now, here come several properties of definite integrals. These are just some things to keep in mind. Some of these properties we've even been using already because they're pretty intuitive. But there's a couple that are not. So let's take a look. This one we've been using already, property number 1. If you have a constant multiple, you can always, we kind of say, move it outside the integral. Just like a derivative, if there's a constant there, it's just going to carry along into your answer. Okay, we've been doing that already. What's the second property? This one we've been doing already as well. We even saw it just a moment ago with x squared plus 1. If you're ever adding or subtracting two functions, then you can take the integral of them separately and add or subtract your results. So we really think of that more like with the antiderivatives. We take the antiderivatives separately and then we just evaluate the whole thing. But, you could even go through the process of evaluating each individual function from a to b if you wanted to, I guess. The third property, now this is an interesting one, and I've got a little drawing here to explain it. If your limits of integration are the same, so I put this is from a to a for f of x dx. No matter what the function, if you're going from a to a, you always get 0. Why is that? Well, remember what this whole thing means, right? It's the area between the function and the x-axis from this number to this number. Well, if those are the same number, there's no area there. There's no width at all. So my drawing is a function, and then from a to a, it's just a line, right? There's 0 area. All right, well, if that ever appears, maybe in homework, you'll know what to do. Okay, let's take a look at this. Oh, I've got a little drawing here as well. Kind of along the same lines, we're playing with the limits of integration. Let's say we've got let's say we've got a definite integral from a to b, f of x, and then we add the definite integral from b to c of the same function. Well, if we go from a to b, and then we just up and go from b to c, we could have just gone from a all the way to c in the first place, right? So the area from a to b plus the area from b to c, why not just go all the way a to c? Now, sometimes it's useful actually to go backwards to have a breaking point in the middle. If you have like piecewise functions and that sort of thing. I don't believe we do any of that in this course. You may see it in Math 122. I can't say for certain if you will or will not. But I think we can all tell, yep, that property is definitely true. Okay, you'll see some homework questions on this. This one I've got another drawing. All right, this one's kind of weird. Again, we're playing with the limits of integration. So let's say, the typical style is to go from A to B. And usually we think of A as being a smaller number than B is, right? So A comes first and B comes second. So what if we were to switch the order? What if we put the B first and the A second, like the A on top? But B is still the bigger number. So the bigger number on bottom, the smaller number on top. So it's like we're working backwards. It turns out that these would be negatives of one another. If you switch the order, the answer becomes negative. So geometrically, that means if you're moving from right to left, then even though this is above the x-axis, moving from right to left causes that answer to be negative. You get like a negative area, which is kind of like what we saw. I mean, there's a similarity to what we saw a moment ago with our negative answer, which is the way I want to conclude here. In the forward direction, the last property, in the forward direction, so thinking from left to right, the area above the x-axis is positive. The area below the x-axis is negative. And so you may even get some cancellation of areas if it crosses through, like we did in that last example. Now you might think, oh, that's a bad thing. If it crosses through, I want to think like total area. Well, you could find the total area if you really wanted to. You could pull off something like what we did here, A to B, and then add B to C, right? If it crosses through, if your function like crosses through there, and here's A, and here's C, we could say, well, that's B, and you could find like the total area of each of them separately, and then think of them both as positive and add them. That's one way around it. It's a good use of that property, actually. However, generally, we actually want the areas to cancel out and to get the net, the sum total of it all, positive and negative. That doesn't make a lot of sense when you're thinking just purely of it as areas. However, we're really not going to, the applications for integrals, we're really not going to think of it as areas, like geometrically speaking. There's going to be a deeper meaning behind what those areas represent in the context of a word problem. So we actually really, really like that area below is negative. Think like positive profit and negative profit, that sort of thing, or like cost and revenue. Like we want those things, we want to get the net total in the end. Okay, we're going to see the meaning of definite integrals at the end of our section here. Next up, told you this was a long section. It's the average value of f of x. So this is almost like kind of like a property. It's tied in there. So what I've got over here is f sub AVE, f average, the average value of the function. Think the average y value can be found with this formula. I've got my definite integral from a to b, f of x dx. But in front, it's being multiplied by 1 over b minus a. So what is up with that? I can find the average value of x really over the interval a to b, be a little bit more clear, the average value of x over that interval. If I take my definite integral and then multiply it by 1 over b minus a. What's going on there? Think of it like this. That definite integral represents the area, right? The average function value, well, that's a height, the height of the function. So what's up with this 1 over b minus a? Well, b minus a, if I take the difference of those two numbers, isn't that the width of my interval? It's like how long it is, right, along the x-axis. So it's like I'm dividing by the width. Well, that makes sense. I mean, isn't height times width equal to area? So if I divide that width over here, like area divided by width, think of a rectangle. Wouldn't I have the height of the rectangle? Okay, that's really weird. Let me make sense of it with a drawing. Then we'll do an example. So here's, kind of my go-to function right there, kind of that roller coaster sort of shape. The area from A to B. Okay, we've seen this who knows how many times by now. We want to know what is the average y value along that part of the curve. So you think, well, it starts pretty high, but then it drops pretty fast. And then it's kind of down here for like almost half of the interval. It's in this low spot. So I'm not sure, like, I don't think it's up high because it drops in so quickly, and it's down here so low. So my guess is the average value would be kind of down here. Here's the way we can think of it. Take that area and flatten it out. So like smooth it out so it's a perfect rectangle, okay? So kind of like that. So you just smooth it out nice and clean, like it's clay. Still from A to B. Then the height of that rectangle would be the average y value. And there's where, our equation comes in. So I've got the width, I've got the height. Width times height equals the area. Now I can take that area and I can, distort it, put it back in the shape of my function if I want. But it's the same area. So my equation still works out. Okay, let's check out an example. Find the average value of f of x on the interval. And I should show you this part too. F of x equals 4x minus 3x squared. And our interval is from -2 to 2. Okay, so here we go. We'll just set this thing up. We're just following the formula, right? So f average, 1 over b minus a. There's my b, there's my a. 2 minus -2. The interval is from -2 to 2 as well. And then I've got my function, 4x plus 3x squared. Looks like I make that plus. I meant to make this plus. Sorry, you guys. 4x plus 3x squared is what I meant to have there. And then my dx. Okay. Well, let's go for it. I think we can do lots of things at once here. So I've got 1 over 4. And then, hey, at the same time, let's do antiderivatives. 4x becomes 2x squared. 3x squared goes back to x to the third from -2 to 2. And okay, now all we got to do is plug in. So I got my 1/4. I'm plugging in the 2. Subtract. Plug in the -2, right? Just going through all the procedure for a fundamental theorem of calculus. The only difference is I've got this 1/4 out front. And here we go to wrap it up. That becomes 16. This just so happens to go to 0. So my average function value is 4. Here's what I will encourage you to do as I end this part of the section. Go into Desmos. I wish we were in class and we could do this together. It'd be so awesome. Go into Desmos, graph this function right here, 4x plus 3x squared. Draw vertical lines, graph vertical lines right? So graph x equals -2 and x equals 2, and it'll give you some vertical lines there. And then have it graph y equals 4 to make that, and that'll, these three will make that rectangle. And then you can kind of look at that original function from -2 to 2, compare it to the rectangle, and just see if you can make sense that the areas are the same. Like, could you take some of the higher part and sort of like, pull it down and kind of smooth it out so it gives you the rectangle that you see. Okay, we're going to stop this video here. We got one more part coming up.